Hello, everyone, and welcome to the National Academy's webinar on life cycle assessment and technoeconomic analysis of emerging greenhouse gas removal technologies. My name is Christopher Jones, and I'll be moderating today's conversation. I'm a professor and the John Brock School Chair in Chemical and Biomolecular Engineering at Georgia Tech. So this is the final conversation in a three-part webinar series from the National Academies on Foundations for a Successful and Responsible Greenhouse Gas Removals Ecosystem, sponsored by the ClimateWorks Foundation. Today's speakers include Morgan Edwards from the University of Wisconsin-Madison, Yuan Yao from Yale University, and Lucia Simonelli from the Carbon Removal Standards Initiative. I'll let each speaker introduce themselves with their opening remarks, and then we'll move into a Q&A period. Audience members can submit questions for our panelists using the Slido interface on the webpage where this conversation is being live streamed. And for anyone using the Slido app or website who has trouble, if there's a code needed, it's GHG Webinar 3. So with that, I'd like to turn things over to Morgan Edwards, who's going to kick us off with her introduction.
Hi, everyone. It's fantastic to be here. I'm really excited to be in conversation today with my two panelists on this exciting topic. So I'm Morgan Edwards. I'm an assistant professor at the La Follette School of Public Affairs at the University of Wisconsin-Madison. I'm also a member of the executive committee of the State of Carbon Dioxide Removal Initiative, which is a global independent scientific assessment of carbon dioxide removal methods and indicators of their progress. And then finally, I contributed a paper on costs and key leverage points of atmospheric methane removal technologies to a recent National Academies report. So I'm coming at this topic from those perspectives. My disciplinary background is in systems modeling and innovation systems. So that's also the lens that I'm bringing in. Really excited to hear from my panelists on LCA, MRV, and other topics. So with my remarks, I wanted to give a little bit of an overview of the greenhouse gas removal ecosystem and some of the state of play, especially as those topics relate to LCA and TEA, the subject that we'll be talking about today. And I think a key kind of point to make up front is that the set of methods for removing greenhouse gases from the atmosphere are very diverse. So they have a common function, a common climate function, but they have very different components and so very different challenges across the topics that we'll be discussing today. And many of these components themselves, or these methods themselves, are also made up of several components that themselves are very, very diverse and different. And so a unique challenge is when we think about looking across the value chains of these methods. So from our latest State of Carbon Dioxide Removal report, some of the high-level takeaways that I think will inform today's discussion. We know that meeting kind of our long-term temperature goals will require rapid reductions in greenhouse gas emissions, but also rapid near-term scaling of carbon dioxide removal. And to scale, or greenhouse gas removal in general, and to scale these methods, we know that innovation needs to intensify. We're seeing a lot of early indicators of innovative activity. So things like grant funding, publications, patents, investments in startups and demonstration projects. And so it's exciting to see this ecosystem rapidly expanding. This is also a source of information and data to inform our assessments of these methods. At the same time, the vast majority of greenhouse gas removal today that is occurring is in the form of kind of conventional, well-established methods. So these are things like afforestation and reforestation. So the more novel methods, which I know are the focus of our conversation today, as of our last assessment, made up less than 0.1% of total removals. So they're growing really rapidly, but they're a really small share today, which means there's a long way to go. And then finally, we know that to increase innovation in greenhouse gas removal, we will need policies to create this demand for these removals. So unlike some other types of innovation where there's a natural good that's being provided, there are many co-benefits for these methods, but primarily they provide a service, a climate service that will require policy intervention to create demand. A second key point is that even though a lot of these methods are very new, there's a lot that we can learn from history. And that's both looking at analogs, so technologies that have played similar roles in the economy in the past, but also even for technologies or methods that themselves are new, many of their components are well established. And so we have a lot that we can learn about those components to inform our LCA and our TEA work. This also means when we're thinking about the economic assessment of these methods, that there's a lot of information we can use to think about the potential for cost declines over time. So there's a large literature that has looked at the kind of features of technologies themselves that tend to be associated with more rapid cost declines. Things like how complex a technology is or how customized it needs to be for a different application. And so we can use that information to develop more nuanced assessments of the potential for declines in these new technologies. It also means that we should be cautious about overestimating the potential for cost declines. So while many of these methods are in the early stages, if some of the components they're based on are more mature or more complex, that suggests the costs may not be able to improve. And that's really important for us as we think about things like setting technology targets, cost targets for innovation. We can also similarly look to history when we think about the conditions for these methods to scale. That's also really important because many of our assessments of these methods will scale non-linearly. So their performance across a number of environmental and economic criteria will depend on the scale of greenhouse gas removals. And we know from many modeling and policy studies that the scale may need to be quite large to address a climate crisis. So we can use these analogs to, again, think about how rapidly these technologies might scale, some potential bottlenecks to scaling, as well as the potential for what's often described as sort of an emergency scaling scenario. So how rapidly might we be able to scale greenhouse gas removal with concerted policy effort? And then finally, a couple points. One is around thinking about, as we're thinking about scaling this removal ecosystem, we also want to think about simultaneously scaling innovation for addressing residual emissions. So we know that greenhouse gas removals can address that part of residual emissions that maybe is most difficult to mitigate. But we want to make sure that our innovation in this space isn't crowding out developments in novel technologies that can help directly address those residual emissions. And then finally, as a modeler, I think as we think towards directions for future work, there's a lot of work to be done integrating more detailed technology perspectives into the kinds of systems models that we use for thinking about pathways for meeting climate policy goals, and in particular in the greenhouse gas removal space, with an eye towards kind of realism of these technologies and representing realistic limits and to their scaling. So I'll stop there.
Great. Thanks, Morgan. Thanks for that intro. So we're going to move now to Yuan Yao.
Thank you, Chris. So I'm really honored to be here today and really grateful for this opportunity to discuss this very important topics with another two wonderful panelists. I'm Yuan Yao. I'm Associate Professor of Industry Ecology and Sustainable Systems in our Center for Industry Ecology at Yale University. So I contributed to the previous National Academy report about the life cycle analysis method. And my own research really focused on life cycle assessment and techno-economic analysis of different carbon removal approaches, mostly related to biomass, like biochar, bioenergy with carbon capture and storage, afforestation, reforestation, and also enhanced rock weathering. So my group developed different kind of model coupling and integration frameworks that's really advanced fundamental LCA methods to better evaluate the GHG mitigation and also environmental impact of different carbon removal approaches, all the way from the process level to those regional, national, or even global level. So we develop a lot of models that really couple LCA and the TEA model with those ecosystem or economic models to achieve those goals. For example, we have evaluated different reforestation, afforestation strategy combined with wood product and biochar in different local contexts like United States and Brazil. We're also looking at the global potential of using wood products that actually can incentivize more forest plantation and actually remove more carbon. We recently developed a machine learning approach that's to really assist the life cycle assessment of biochar made from different biomass feedstock at the global level. And we also develop all kinds of models for enhanced rock weathering with different supply chain configurations in different regions. So our past projects in my research group across different topics really find that the GHG mitigation efficacy and other environmental impact like eutrophication of different CDR strategies really vary substantially by location and time. So even for the same strategy, implementing them at the different locations with different time frame consideration may deliver very different outcome. So we find the need to really develop region-specific strategy if we want to use different carbon removal approaches to not only just mitigate GHG emissions, but also considering all kind of a co-benefit that can make the most valuable contributions to our overall sustainability goal. So early this year, I published a paper in Environmental Science and Technology Journal, which we analyzed LCA studies and also monitoring, reporting, and verification, we call them MRV, protocols currently used in the voluntary carbon market. And we really identified some critical gaps in the LCA literature that are very crucial for reliable MRV for carbon credit. For example, we find the lack of consideration of timing and permanence, and also the lack of scaling information in many LCA that will be very useful for project level GHG accounting. We also find some gaps in the current MRV protocols currently used in the market. For example, and especially for those gaps that LCA community can provide support. For example, developing some criteria for environmental safeguard, and also use more comprehensive GHG emission factors that can consider not only CO2, but also other non-CO2 gases, and also include the full life cycle system boundary. We also see how different MRV protocols using different assumptions, methodologies, and data, even for the same CDR. So there's a really need to harmonize across different protocols. And there are two areas that I think both LCA and MRV community really needs to address together. That is to develop a very robust method for co-benefit and also land use change impact, because many carbon removal strategies does involve the use of land. And I think the collaboration between the LCA and the CDR community is really essential for developing these robust frameworks to support the carbon market and policy making. And as we move forward into this panel discussion, I would be happy to dive deeper and share more. Look forward to our panel discussion.
Thank you, Yuan. So we'll now move to Lucia, who will share her thoughts.
Thank you so much. I am also very honored to be here and look forward to learning from my amazing other panelists and your questions. I am Lucia. I'm the Director of Programs at the Carbon Removal Standards Initiative, or CERSI. We are a nonprofit that uses science and policy to unlock carbon removal opportunities across society. Founded on the idea, much like how Morgan articulated it, that carbon removal is a public good and it will largely be driven by policy. And where we find ourselves today, the state of play is really that carbon removal's lifeline is the voluntary carbon market. It is the major source of demand and innovation support. And we're seeing, excitingly, a lot of those structures being translated into emerging compliance markets around the world. That is critical work and the focus of a lot of the CDR ecosystem policy advocacy. CERSI is looking at the complement of that because even in the most generous projections, the amount of demand that markets, both voluntary and compliance, can generate are bounded well below what even the most conservative estimates for residuals will be in 2050. So it really begs the question, what will demand be? And what does it look like? What form does this take? So what we are trying to do is map out across society where carbon removal processes can be integrated into existing infrastructure, activities, industries, sectors, from heavy industry to agriculture to environmental remediation to adaptation, and match these to the regulatory and policy context that already exists for these areas. So how do we tweak what exists to incorporate carbon removal rather than just also relying on standalone climate policy or carbon removal, policy vehicles? And then ultimately, how do we measure the carbon removal appropriately within these contexts? So to come back to, the LCA and MRV framing of this webinar, LCAs are incredibly important to understand the full footprint of a carbon removal process. But the container of the LCA or the boundaries of the LCA are, sometimes context dependent. If we take the example of, say, direct air capture, which is a closed system, relatively easy MRV, on the voluntary market, it's critical that the full LCA is really understood well, because there's a claim that for a credit sold, you're neutralizing some ton of emissions. if we look at this direct air capture plant in the context of a compliance market, say it's integrated into an industrial complex and it's sort of symbiotically working with a chemical plant. It might be that in that context, that plant is part of the heavy industry regulation and the accounting happens in that setting. But the emissions from the energy production upstream are governed separately under a different regulation for the power sector. So we've now spliced that LCA, it's governed by different parts of the regulation, and might, be subject to different accounting. So you can imagine, as we're talking about weaving carbon removal across society, and we are even introducing the added complexity of open systems, how we splice up that LCA might depend on the regulatory and policy context that govern each piece of it. And so we have more of a distributed quantification situation here where it has to match those contexts. And so harmonization is an important question, but it's also a question of what does that mean when we have such a interwoven system of carbon removal processes. So I am extremely excited to have this conversation, and thankful for the National Academies for hosting this event. I'll stop there. Thank you.
All right, thank you for those introductions. So we heard about the huge diversity of methods that are available for greenhouse gas removals and the challenges that those bring. We heard about how the efficiency of technologies can vary based on location and time. And we also know that the likely size of the market demand is not going to be matched to the scale of implementation that will be needed for large-scale climate change mitigation. So given those introductory remarks that we heard, let me address a couple questions to the panel and hear their thoughts. So we'll begin by asking about the current developments in prospective ex-ante LCA for these emerging technologies, and how did these apply to carbon dioxide, methane, and other greenhouse gas removal approaches. Maybe we can start with either Morgan or Yuan here, and then we'll move through some additional questions as well.
Maybe I can start?
Sure.
Yeah. So for many emerging technologies, doing such LCA and TEA for them is very challenging, mostly because lack of the inventory data, because they haven't been scaled up. So we need the data to at least know methane and energy balances, what are the GHG emissions generated from those processes. And there are a lot of engineers using those engineering process simulations, like I'm a chemical engineer by training. So we do a lot of process simulation for those gasification, pyrolysis, for the biomass treatment, so we can understand if we scale them up to a certain capacity, what are the potential mass and energy balance would be, and use this data to feed into the LCA and the TEA to do the analysis. Recent year, we also have those development of consequential LCA that's really considered the possible changes in the market, in the policy, and looking at the overall consequences of the system. And many times, this kind of analysis also incorporate those economic models, or some of them using integrated assessment model. Like my group use some integrated assessment model and couple with LCA together. And as I mentioned in my open remark, like many times those impacts vary by the location and time. So we see a trend of more and more like a dynamic and also regionalized LCA and TEA study that really try to looking at those temporal and spatial variations in the future, if we can scale up some of those emerging technologies. I also see some study using the learning curve to try to consider possible improvement in those technology when you scale up. And because I specifically working on those carbon removal related to biomass, so in our field, we do have a lot of efforts in trying to couple those LCA and TEA model with ecosystem modeling and economic model, so we can look at those dynamic interactions among the market, industries, and ecosystem, and we can better understand how those ecosystem may respond, and consider possible land use change impact when we use those biomass for the carbon removal purpose.
So I would also echo some of what Yuan said, I think, and your group is at the forefront of a lot of this consequential analysis of life cycle impacts of CDR. A couple other things that I'll note, I think there's a lot of opportunity for innovation, both kind of looking more granularly at the component level. And there's a lot that we can learn, even if we don't have good data on an existing system, kind of using analogs from other systems that do exist. So I think really going deeper and looking at the individual components and the features of those components, and in particular, what we know from how they interact with social and political systems. So bringing not just technical information, but understanding how these technologies their features might be predictive of their ability to scale or how they'll interact in social systems. I think on the opposite side, and maybe this is sort of a meso level in between the systems level that Yuan was talking about and the technology level, is thinking a lot about multi-technology assessments. So within the CDR landscape, we have methods that may be competing for the same resource, something like CO2 transport or geologic storage. And at the same time, we also might have components where innovation directed at one method could also see benefits and cost reductions in terms of other methods. So I think as we're thinking about really understanding the economics and the environmental impacts of this broader greenhouse gas removal ecosystem, I think moving from method by method assessments to a more holistic picture will give us a lot of insight, especially as we think about these methods scaling.
All right, thank you both for those remarks. So I want to pivot towards MRV. So thinking about the developments that are needed in measurement, reporting, and verification for GHG removal, it's important that those methods provide good durability and reliability. What is your assessment of how current MRV methods are mature or not mature for different types of methodologies today? Anybody want to tackle that? Let's maybe start with Yuan, and then we can see if Lucia has some things to add.
Yeah, happy to start. I think one area we did find when we review those MRV protocol is they definitely need some harmonization across protocols. And I agree with Lucia, we also need to define what do we mean when we say harmonization. But for that one, a study we're specifically looking at is we do find that the different protocol, basically when they use some GHG emission factors, those factors could have very different system boundaries and assumptions across different protocol, even for the same carbon removal technology. And you would imagine using different factors, you would get different carbon credit. And we do find like some of the protocol, when they do this GHG counting, they only consider CO2, while the others, they consider many non-CO2 gases. And for some carbon removal, they could have some emission like methane that definitely contribute to large global warming potential. System boundaries, the one Lucia previously mentioned, are pretty important. So if you look at different protocol, you can also find that some of them have a different system boundary about what system you should be included, while the others, they don't consider them or they don't mention at all. And of course, when you include different activities, your carbon credit estimation would be very different. And I think another important thing is about the baseline, because baseline will help determine the additionality when we want to issue any kind of carbon credit. So if the baseline across different protocols are different, then it is very hard to compare when you have the same carbon removal project, but estimated using different protocols. Another one I also want to emphasize is the consideration of co-benefit. I'm not saying like we have to always add the co-benefit into the GHG accounting, because some co-benefit relate to GHG emissions, some maybe not. But I think considering those co-benefit into the MRV is very important, because for some carbon removal, removing carbon would be one very important motivation for people to adopt them, but not always the cases. They may have some co-benefit that would be appealing to different stakeholders who want to adopt those technology. And by the way, they also remove carbon. So if there's a way we can really include those co-benefits, recognize them, and quantify them in the MRV, I think that will be very helpful to really accelerate the adoption of different carbon removal strategies. I will stop here. Let's see whether Lucia has some other insight.
Yeah, very, very aligned one on the co-benefit piece. So maybe I'll start there since that's where we left off. Is that when we are thinking about how do we integrate CDR into processes, likely the policy and regulatory frameworks we're dealing with are things that are actually governing what we would call the co-benefit in a carbon market setting. But that actually becomes the central thing that we want to measure or value. In the enhanced weathering context, for example, if we're thinking about pH management policies, the agronomic benefits, in particular the pH enhancements, are what would be measured, right? That's what would be of central importance. So then looking at the carbon removal MRV as piggybacking onto how do we leverage existing data collection or leverage those existing ways of measuring agronomic benefits, can we also integrate the carbon removal measurement? So there's also an efficiency aspect of leveraging some of the measurements of these co-benefits when you're in a policy context too. In addition, I also agree, we need to think about different spatial and temporal scales from a policy-driven standpoint. Again, the example of enhanced weathering, if we could think about regional or national level subsidies, we're talking about much different context than a project attribution that has to deliver credits in a certain amount of time. So we have a different way potentially of constructing deployments and study design and reducing uncertainty in those contexts. And then the last thing I'll say is that I think looking at the future of what demand looks like is so important, and matching the MRV and the innovation needed to get there. Recently, our executive director, Anu Khan, along with academic partners, released a preprint talking about, how we could potentially measure enhanced weathering and alkalinity fluxes at the watershed scale. And that would be great, right? That would be very efficient, cost effective. There are a lot of knowledge and data gaps to getting there. But if we see that as an optimal place or a potentially optimal place where MRV could be in the coming decades, then really crafting projects today, like the projects on the VCM, to have components of learning that are really directionally significant for these policy pathways to scale. It's not just about the technological and resource barriers, it's also about the policy context that will sustain them. So crafting these projects to answer some of these MRV questions that are in service of longer term goals or longer term aspirational ways of seeing MRV in the future.
I'll maybe just build on what Lucia was saying. I think thinking about MRV as a core part of the value chain of these methods, and really estimating the cost of MRV for each method will be an important part for understanding how these methods compare to one another and how we might scale them. So just like in technoeconomic assessment, there's a focus on the individual engineering cost components. I think really understanding what would be the cost of monitoring, and also how might we have innovation there to have cost declines will be an important piece when we're thinking about kind of looking at the overall ecosystem and comparing methods to one another.
Great, thanks for those comments, everyone. So we heard earlier about the huge diversity in methods that are available for greenhouse gas removal. And they could be engineered systems focusing on carbon dioxide or methane. They could be natural systems involving biomass or rocks. But there's also land-based methods versus marine methods. Can you comment in general on the relative maturity in these different fields, and how do the different methodologies currently compare to each other from a perspective of LCA or MRV? Is there one area that's particularly mature compared to others? And I know that's a wide open question, but I think there's a lot of questions in the chat that are related to this. Who wants to kick us off? I'll maybe ask Yuan to start from her perspective on the biomass side, because she's already spoken a little bit about that, and then we can build off of that with the others.
Yeah, my sense is those land-based will be much more mature than those marine-based, just looking at the number of literature LCA, TEA study have published. And for those land-based, as Morgan previously mentioned, like if you're looking at the current mature projects in the carbon market, like those reforestation, afforestation, if you go through those projects, a lot of them are related to this. So a lot of land-based, I think they are much more mature than those marine-based. And for those marine-based, I haven't seen many studies, and maybe there are one or few, but their number of literature are much smaller. And when we're looking at those carbon removal strategy applied to different ecosystems, I think we really need to have a tailored assessment strategy because those ecosystems respond very differently. Like I majorly work on those biomass systems, like related to those land-based ecosystem. They are definitely highly dynamic, changing with the location and time I mentioned before. And they also have a different carbon pool. Like if you're looking at above ground, below ground, they respond differently. If you are using different part of trees, and also many times when we're looking at those land-based carbon removal, people are very interested in those waste, like forest and agricultural residues, because people assume like they're currently wasted. So if we use them, they could be environmentally burden-free. However, our previous research really shows that removing them actually would reduce the carbon input to soil. So if we account for those potential soil carbon disturbance, then their overall performance may be different. I think this also may be applied to marine-based CDR, like we need to consider how the marine ecosystem may respond. And also another one related to land-based carbon removal a lot is the leakage, especially for economic leakage. Like when you use some biomass here, they may cause some biomass system changes in other areas that may end up eating more greenhouse gas emissions. And many times consider those economic ecological system leakage require not only consider the ecosystem, but also how the global market may respond. So that's add a additional complexity for this land-based carbon removal strategies.
Anybody else want to have a run at this one, or do you want me to jump to another question?
I can add a couple more thoughts. I agree with what Yuan said. I think this is also very difficult to answer for a lot of methods, especially if they may be more mature in some applications than the applications that we have in mind with greenhouse gas removal. And so this came up a lot when we were looking, like assessing the technology readiness level of different atmospheric methane removal methods, where some of them have been applied in other contexts, potentially in contexts with much higher methane concentrations than ambient concentrations. And so it's often a complicated question to then describe these. Many of these are very, very early stage in the application of atmospheric greenhouse gas removal, but are more advanced in other kinds of specialized applications, maybe at higher concentrations of the gases. So that means they potentially have an opportunity to scale relatively quickly. Another kind of general point is that what we've seen from kind of the data on investment and activity around startups is that this landscape can change really quickly. And so we saw that, for example, with like a surge in emergence in biochar. So we can sometimes have an idea that we think we know the state of play across these different methods, and then there can be this rapid change.
All right, so I want to move over to Lucia, and she already spoke a little bit about MRV in the context of policy versus a carbon market. But then to build on that from the chat, there's a question that says that if carbon removal is a public good, how can its benefits be priced in absent the government doing it?
Yeah, I mean, it's a good question. Probably the government has to do it, like waste management in other contexts. But the way in which it's priced in is variable, and I think can be done creatively and resiliently. And it's not just about creating revenue streams for credits. That's one aspect. But there are other ways to do this. In particular, again, talking about the co-benefits, I think that in the context of enhanced weathering, for example, there are real potential agronomic benefits. And so if the carbon removal pathway is scaled through that as a mechanism that's valued, then it's also returning a value to farmers and to society. And the return on investment that the government is putting in is reaped in many ways. So I think it is true that there's going to need to be financial subsidies in some way and form, most likely, the government driven. But I think they look very different than I think we perceive of the government as just buying tons of CDR. It can look like a lot of these other things that are integrated into processes and bringing different types or elevating different types of co-benefits.
Thank you, Lucia.
I could maybe also add, so I think we also have seen a lot of corporate activity around purchases of carbon dioxide removal. And so that activity alone won't bring us to the scale that we need to address the climate crisis, but these advanced market commitments, especially for really early innovation, can be a really important market signal. So ultimately, we will need a strong policy demand signal, but there are also other roles that other actors can play that can help kind of innovation and scaling. Also, I think building on what Lucia was saying, there are different roles that greenhouse gas removal can play at kind of different stages in our climate policy. And even with policy incentives, I think thinking about the mechanisms for incentivizing greenhouse gas removal, looks very different when you're thinking about trying to reach net zero and then when you're trying to reach net negative and sort of draw down historical contributions. And I think the policy mechanisms for doing that may be more challenging than for just reaching net zero.
Great, thank you both. Sticking with Morgan for a moment, can you comment a little bit on how the LCA and MRV needs change depending on the greenhouse gas being considered? So whether, for example, it's carbon dioxide or methane or other greenhouse gases, what are your thoughts there?
So I think there are different ways that we can divide up the distinction. So I think another really key distinction that we've already touched on is these open and closed systems, which we can have open and closed methane removal systems, and we can have open and closed carbon dioxide removal systems. But I think on thinking to non-CO2 greenhouse gases, I think one key issue is thinking about the need for long-term monitoring. So that's something where with atmospheric methane removal, which might be destruction or conversion, we may not need to be able to monitor in the long term, whereas with some of these carbon dioxide removal methods, especially if they're sort of land-based storage, we might need to monitor them for risk of reversals for a very, very long time period. And so that requires different kinds of governance structures. And then I think more generally, thinking about how we compare the climate impacts of these different greenhouse gases can be really important. So methane being higher potency, but relatively shorter lived compared to carbon dioxide. So especially when we think about using these removals as a way to offset some other contribution to climate change, thinking really carefully about how we're doing those calculations will be really important. And a general recommendation is to try to have a no regret strategy, meaning that if you're trying to offset a high potency but short-lived gas, you want to make sure that your removals match that shorter term impact. And then vice versa for very, very long-lived greenhouse gases, where we want to make sure that we're not leaving a legacy of very long-term warming by not sufficiently removing enough, whether carbon dioxide or methane from the atmosphere.
Thank you. Thank you for that. Okay, so to another audience question, getting into some of the nitty-gritty of performing LCAs. So in some LCAs, we allocate emissions to multiple functions. Can we do that in multifunctional CDR systems? For example, one example would be bioethanol plus CCS. Could you allocate some emissions to ethanol, to CDR, to oil and other products? Yes or no? And if no, why not? Anybody want to take a stab at this? Do we like to split allocations in the CDR space, or is that something that's not done as often as in other fields?
I think based on the protocol we have reviewed previously, some protocol allowed allocation if you have the multiple product, while the others say you need to figure out what are those activities directly related to the carbon removal outcome and only account for those emissions. So and I also see some protocols keep it very vague, just say refer to the LCA ISO standard, which actually propose several different allocation methods. But you can also avoid allocation if you can really figure out which activity is responsible for which product. So I guess this go back to the previous one we discussed is, I don't think this is the place this panel discussion is not the place we try to get a consensus about which one is the best methodology. But I think we need to make effort on this direction to really looking at for different greenhouse gas removal systems and a strategy. If they produce multiple products, what may be the best way that introduce the less uncertainty and it can be more robust for assessment. we may need to have a different strategy for different technology rather than just to figure out one allocation method and say it would fit all of them.
All right, thank you for that. Following up with a question for you, Yuan, from the audience, how should practitioners think about indirect land use change and inaccuracies of these estimates for certain products? How prevalent is that a problem that researchers are currently working on?
Yes. So indirect land use change, those induced by the market, is really a headache. Whenever we do the LCA involved biomass, especially if you are using the dedicated biomass rather than residues that are less likely to cause land use change. So currently, a lot of numbers you can find related to indirect land use change in those policy or LCA study. Most of the time, they get those numbers by running different integrated assessment model or those large scale economic model bundled with some ecosystem models. And I can tell you, if you look at different models, they may give different numbers. So currently, some of the policy, what they try to do is they try to get the number from different models and average them. I will not say that's the best approach because different models make different assumptions. So currently, my group actually have an ongoing research project. We try to looking at the different models and also at the different demand level, how those induced land use change may be different, because those induced land change basically reflect how your landowner's decision may be changed in responses to those demand changes in the market. So we want to look at how large those differences would be. So I would say that's a headache problem, but there are a lot of research already ongoing. And I hope in the future, at least for different type of the biomass, we could have some consensus on for different demand level, what are the possible ranges of GHG emission or other environmental consequences would be if we consider those indirect land use change. So stay tuned for those LCA practitioners.
Thank you, Yuan. I want to turn to Lucia for a moment and ask, what do you think would be the highest impact advancements in data collection and sharing infrastructures for MRV in the greenhouse gas removal space? And how can the LCA community support these advancements?
Yeah, I did sort of touch on this a little bit earlier in terms of leveraging public data collection and data sets as much as possible. But I think a resounding answer is probably more data and more shareable data. And that often comes in conflict with the realities of, the private sector and startups, and there's tensions there that are very understandable. I think in particular for open systems, though, we really do need robust data sets over time. If we look to lessons learned from forestry, for example, a lot of good projects rely on public data sets for baselining and for controls. So I think that, we can try to mimic that in some of these more emerging pathways. There are jurisdictions that support and require public soil health cards, for example, in terms of collecting that baseline data. Also, I mentioned the watershed level monitoring before. There are water quality monitoring networks. In the US, there's the USGS gauge station system. So there are, I think, questions of what data we need, of course, and how do we process that data. But I think in terms of collecting it and sharing it, I think those are big obstacles too. And looking as much as possible to leveraging that public infrastructure will be important.
Thank you very much. So cycling back to some the LCA questions, how should a practitioner think about attributional versus consequential LCA in this space? Are there any considerations that might be unique to the greenhouse gas removal space? Morgan or Yuan?
I'm happy to jump in first with some thoughts. I think one piece that's potentially more unique for the greenhouse gas removal space is the conversation around mitigation deterrence. So when we're going from thinking about attributing removals to a given method to thinking about the role that method is playing in a particular policy, we want to ensure that we're not creating perverse incentives to reduce the amount of mitigation that's being done directly. I think an example that came up when we were thinking about the question of atmospheric methane removal is there are a lot of relatively low cost but underutilized opportunities to directly reduce methane emissions at the source. A bad outcome would be if early methane removal was targeted towards those emission sources where we already have cost-effective pathways for direct mitigation. So I think that's something that comes up when we move from kind of an attributional assessment of the technology to thinking about consequentially what role is it playing given policy incentives. And so I think we want to think carefully about making sure that we're incentivizing early removals and sort of these high impact opportunities where we otherwise don't have good mitigation options available.
Great, thanks, Morgan. So another question from the audience. This is connecting our greenhouse gas removal topic to other areas of the energy and climate ecosystem. Does anybody know about the quality of the LCA data that are available for any critical minerals that are used in CDR or used in greenhouse gas removal? Do we have robust knowledge and robust data there, or is that an emerging area at this time?
I think that depends on what type of the critical mineral you are looking at. Some of the critical mineral, for example, those listed by the US Department of Energy that has critical materials, there are many of them in the past to receive a lot of funding on those. They have a lot of LCA study published. But for some type of the critical minerals, if they are really used in a very small amount and don't have much data, I suspect maybe those LCA data would be very limited.
I think this is also an area where like the consequential approach can be really important. So many of these closed systems for greenhouse gas removal are extremely energy intensive. And so then you're having this tight connection between an assessment of the environmental impacts of whatever your energy source is and the environmental impacts of your greenhouse gas removal method. And so there, I think there's a broad literature talking about critical minerals and energy systems as these systems scale, but I think just recognizing how much energy might go towards something like direct air capture, if that is a primary method that is used for carbon dioxide removal, like just these scales are enormous. And so I think even though we have a lot of robust studies on those critical materials and their potential impacts, really thinking about the additional impact of this large energy demand source from CDR will be really important.
Thank you, Morgan. We'll do maybe one or two more questions, and then as we get towards the end of the hour, I may ask each of you to kind of sum up your thoughts based on everything you've heard in a minute or so. But this next question is about the potential for LCA and TEA to enhance the rate of scaling of these technologies. So we talked at the very beginning of the discussion about the huge diversity in technologies and approaches that are out there. And some are evolving more quickly than others. Do you think there's a role for LCA and TEA to support the faster scaling and the research and development in this space?
Maybe I can start.
Go ahead.
Yeah, I do think LCA and TEA can be helpful. So one is LCA can really help us to at least understand the potential for the GHG removal for a certain technology if we scale them at different level. And in the recent year, there are a lot of people also couple LCA with those large scale models, so we even can understand the regional or even global level potential of those technology. I think those big numbers will be very helpful, especially for stakeholders outside this technology area to understand the potential of those technology. Another one is when we do LCA and TEA, many times we do those hotspot analysis, right? So we really try to understand the drivers of the major cost or the environmental burdens. And I think those are really helpful to help the researchers to identify those key parameters or areas for future improvement. So they know how they can better improve their system for the maximum level of the benefit. So another one is, as I mentioned, many impacts are really varied by region. So many times when we do those regionalized analysis, we may be able to identify there are some regions that will be more suitable for a faster implementation of those strategies than the other regions. So we can make all of our effort focus on those regions first.
I'll maybe add also what might be a little bit of a cautionary warning is that we see in the history of a lot of innovation systems where initially you have this diversity of different technologies, and then eventually there's sort of a coalescence around a dominant design. And I think one thing that we've learned is we don't want to coalesce around that dominant design too early, which is to say, so we do want to be using techno-economic analysis to inform the direction of innovation, and to think about these sort of high leverage points that Yuan was talking about. But I think we also don't want to coalesce too quickly. I think that the diversity of methods for greenhouse gas removal is actually a large strength in this area, and we want to continue promoting that diversity of methods because ultimately we don't yet know which ones are most likely to be able to scale. We can guess, but we don't know.
Thank you, Morgan and Yuan. So we've talked earlier about the different types of data sets that we can bring to bear on this problem. Would anyone like to comment on how dynamic emissions accounting, in particular temporal aspects, are being used or can be used within LCA to assess the effectiveness and climate impact of a particular type of CDR? And how is this related to the cumulative emissions budgets?
I can talk about it since my group also work on dynamic LCA and GHG accounting. So there are many different dynamic accounting methods being developed. So many times people consider when we incorporate, and any way we can incorporate the temporal dimension, we can call it dynamic. So if you're looking at those landscape of the dynamic LCA, you will see people that incorporate the dynamic inventory data. That means that for some technology, maybe each year, their emissions are different. There are also other type of dynamic LCA accounting that included dynamic GWP factors. That means when your emission emitted this year versus your GHG emission emitted next year, their impact within a certain time frame, they are different. And there are, of course, more integrated dynamic methods that include both the inventory data and also dynamic GWP method. I think the current issue is there are so many dynamic methods being developed. So currently there's no consensus to say, for one specific technology, which one may be best to consider those temporal dynamics, because we don't want to use a more complicated method just because it's more complicated. We want to use a more complicated method because it can more robustly assess the impact we have. So I think some more effort will need to be done really around this area to understand what new insight can offered by this dynamic method when we apply to different technology. And we focus on those technology where using dynamic method can really review those novel insights or overlook the opportunities where the static method cannot achieve.
Thank you. All right, so one more question, and then I'll ask each of you to give a brief summary thought. And this, again, is from the panelists. They'd like to hear about how LCA experts can better interact with cost and scale analyses, because for both TEAs and integrated assessment models, LCA considerations are often not considered, and that can be a big problem for people who are working on planning and policy making and other factors. So if anybody would like to offer a thought on that, we will then cycle into brief closing remarks from each of our panelists.
I can talk again, but I feel I talk too much.
Jump in, and then someone can fill in any gaps that they think you might have left.
I think a close collaboration is very important because my own group do LCA to TEA. We also use integrated assessment model and really try to incorporate those market dynamics, cost consideration into LCA. But there's a very high learning curve for me and all of my students if we don't have a really patient collaborators to teach us how to use those very complicated integrated assessment models. And I happen to also have an economic colleague who is very patient to teach us everything about market economics. But I couldn't imagine how slow our progress would be without those collaborators. So I think we really need to have more communications and collaborations between those different disciplines. And of course, if there are more funding, can support such interdisciplinary, cross-disciplinary collaboration, that's really helpful. And I think once we have more and more collaboration, demonstration, and case studies, then maybe at one point we can develop some standardized method or framework that can really disseminate it to the whole community, so practitioners can know how they can better incorporate those insights from different large-scale models into LCA.
I was going to echo what Yuan said, that I thought about, this is a great question, and I thought about it from the flip side, and as a modeler, like what can we do better to better incorporate insights from LCA? And I'll say one broader challenge is that these models are often developed to answer questions at the level of like national or international climate governance. And so there's a lot of work to be done to really be able to tailor the results. Like as Juan said, these models are they're very complicated. They're difficult to run. There's a big startup cost, to really being able to tailor to the kinds of questions that might be asked at the project level by technology developers, or by companies who are asking questions about the mitigation potential of different technologies. So I think that's also an area of like ripe for future work.
Great. So thank you, Yuan, Morgan, and Lucia. We had some really interesting questions from the audience, so I appreciate all of you commenting on those. I'd now like to ask each of you in a minute or so to give some summarizing thoughts. So you've heard a lot of different thoughts and comments from the panelists, and if you want to leave the audience with any key thoughts from your perspective, and maybe we'll start off with Lucia.
Great, and thank you again for having me, and for everyone for attending. I have two closing thoughts to share. One is, again, I think we're thinking about MRV in a very fit for purpose way, and I think if we're going to scale carbon removal, we have to be creative and integrated. So, I think I do wonder, like, what does harmony look like in that context? I think the second thing also, which we discussed a little bit less, but is that a lot of the MRV and even LCA work around open systems, which are a really emerging space in carbon removal, really boil down to what is our tolerance for uncertainty. And that uncertainty discussion is of incredible importance. And I think is difficult as we translate certain policies that were really built for closed systems now to start integrating and including open systems. And that the way we design our studies, that influences the robustness of the statistical inferences that we're making in order to make the claims about the carbon removal. So I would say uncertainty is a major theme, and I would advocate for empirical measurement as long as possible and not premature moving to modeling. So stop there.
Thank you, Lucia. I appreciate those comments. Very pointed, two great comments. Morgan, let's jump to you.
I would echo what Lucia said about uncertainty. I think this is a really fundamental question as we're thinking about different greenhouse gas removal methods that have very different kind of inherent levels of certainty that we might have. I think my overall reflection on our discussion is really this importance of scale. So where we are right now is very early in terms of the amount of greenhouse gas removal that we will need to be able to meet climate goals. And that comes up in a lot of ways. It comes up when we think about conducting life cycle assessments and technoeconomic analyses, looking at a plant or a project as it exists today. Those impacts would be very different looking at that same project in the future, both because of innovation, but also just because of all of these nonlinear effects that we've been talking about in terms of the impacts of these methods. So I think this is a general takeaway when thinking about like addressing the scale of this challenge, but just from where we are now to where we will be is a massive transformation of social systems and political systems and environments that we're envisioning. And so I think really being mindful of that scale as we go about these assessments, I think will be really important. And with that, thinking about the importance of early action now. So we know that in order for these technologies to be able to scale up, we need to be developing them robustly from the beginning. And so making sure that we're balancing these really, really robust and rigorous kind of monitoring with also like robust encouragement to scale and try things.
Thank you, Morgan. On to Yuan.
Yes, I fully agree with what Lucia and Morgan mentioned. So I will just mention 2 points. One is I'm really enjoying our conversation today about the co-benefit, which are super important. We definitely need more field data to understand the quantity of those co-benefit, but I think we also need to have robust methodology to incorporate those co-benefit into the LCA and the TEA. Because I think that those modeling practice can really help us to understand when we have a long list of different kind of co-benefit, which may be the one that's obviously most important and should focus of the future MRV. The second one is I think we always need to have tailored modeling strategy. No longer we're using LCA, TEA, GHG accounting, or integrated assessment model for different kind of technology, and also depend on who are the decision maker or the stakeholder that will use our result. There are some cases maybe the need for policymaker will be very different for the people who purchase the carbon credit. And we really need to understand what is the best modeling strategy in the most robust way can deliver the insight that would be important for their decision making.
Wonderful. Okay, thank you for all of your comments. I'd like to wrap up our program by thanking all of our panelists for their time and also the audience for their thoughtful questions. We got to as many as we possibly could. Thank you again to the ClimateWorks Foundation for their support and to all of you in the audience for joining this National Academy's webinar series. Best wishes to all. Thanks for attending. Bye-bye.